Okay, today in this session we'll be mainly talking about MATLAB tutorial, and this is as a refreshment basically of what we did up to now. This is kind of refreshment of what we did until now, but using the software, using MATLAB. After it, we'll start talking mainly about design with frequency response, using body diagram to design controllers, as we did using root locus to design controller. Now using Bode Plot to design controller, lead and lag controller. Before starting this, let's do a refreshment or wrap up of what we did up to now via a tutorial, MATLAB tutorial. Basically, this MATLAB tutorial, I took it from MATLAB TED Talk. If you go to MATLAB TED Talk, you'll find a lot of things, interesting things. Mainly in control for electrical and control in general for motors. Control in general, you can click on it and go to the control tech talks. You'll find a lot of interesting things in control, like robust control, state space, predictive maintenance, and other stuff. Those are things you could look for. They are many of them, but not all, will be seeing in modern control, like state space we'll be seeing in modern control. If we are lucky, we'll look at predictive control. We should have predictive control somewhere. Yeah, modern predictive control. So it is something we could look at. Kalman filter, hopefully we could see in modern control class. And those are basically robust control, of course, state space. Robust control, we may see it as well. So it's basically subject of modern control. Otherwise, everything else, many of them we saw, like reinforcement learning, we don't talk about. But like this kind of control, basic control, we saw. So you could also look at all of them. So now we are interested to talk about Bode Plot, and basically you can click here. You have 5 videos using Bode Plot and understanding Bode Plot. You have 4. So I will go with you on understanding Bode Plot, these 4 videos, and your tutorial that you have on your Moodle is basically from understanding Bode Plot tutorial. So if I click on understanding Bode Plot tutorial, let me click on it. Alright, so you have 4 parts. Okay, I'll go over them, all of them. Like this is part 2, part 1, well, I'm not going to look at. So you have part 2, part 3, and part 4. I recommend you to look at them yourself. What we'll do now is just only the part which is related to using MATLAB. But I recommend you to watch all the videos yourself. Also, in addition to the control or MATLAB Tech Talk in general, and more particularly controls, I recommend you also to look at the YouTube channel of MATLAB. You'll find machine learning, you'll find predictive maintenance, state space, deep learning. You'll find interesting stuff. Okay, and their channel, you can go to the playlist and find many playlists. Of course, something related to what you are doing, so I recommend you to go and look at them. Let's start this MATLAB tutorial together. Okay, in here I'm defining a function. Alright, and this function is, they call it G system, and it's equal to 400 over s square plus 10s plus 400, of course, and I can simply, as you know, I say GSys, and I get my Bode Plot. So busy, the system is busy. And this is your Bode plot. Of course, from it you can get some minimum stability margin or all stability margin. So peak response, we know that this is the peak response. It has 6.3 decibel at 18.7 crossover frequency. So I know that this is a crossover frequency. Okay, what is the minimum stability margin? Okay, here is the phase margin is the minimum stability margin, which is 41.4 degree, and you know how to find it, how far we are from the 180. And the system, it tells you if it's stable on closed loop or not. It is above the 180, so it means it's stable. It should have both above the 180. So now if you look to the, better recommend to go to the all stability margin and look to the all stability margin. At zero crossover frequency you have this. At minus 180 it doesn't cross, so you have infinity gain margin. So that's why the minimum, in this case the minimum stability margin is the only stability margin. Why is this the minimum? Because infinity compared to 41.4, so the other one, this is the minimum then. So if you take it over and you say it's all stability margin, it's the only one you have. Okay, system is stable. Let's see what else in the tutorial. Okay, it seems here they opened the control system designer app. So you go to your app. Okay, that's how it opened. Well, now I don't want this. Also, I don't want this. I only keep this over the entire system. So, first of all, what you see is for a system G equal to 1. So your system G is equal to 1. Here you have, the architecture, you have the G, you have the C, H, all by default are 1. And that's why you can see the magnitude is 0 and the phase is 0. Alright, so let's see what they will doing now. So they add a pole, they go and add a pole at around 1 radian per second. So let's go and do this. I click on it, I find the Bode editor, I'll go and add a pole at 1 radian per second. So basically here, if I add my pole here, so look at the system how it will look like. So here, just verify, it is 0.9, the frequency is 0.9. I'll put it 1 as we said. So I want to add it at 1 radian per second. So what is this that you are actually seeing here? Okay, I added a controller, I added a pole at 1 radian per second, 10 to the power 0, so on. So this is what actually, if you remember how to draw a first order system, you go to your chapter PDF Bode diagram for first order system. That's the general formula of it. And the crossover frequency is 1 over T, right? So 1 over T is your crossover frequency. Basically, this means what? 1 over 1 S plus 1. That's the general form of it. So it tells you what? It tells you that the crossover frequency is than 1. Alright? So if you want a crossover frequency at 2, for example, now if I put it at 2, so then gonna be 0.5 S. Okay, if I want to put it at 2, you see 1, this becomes 2. So now in this case, this will become 2, and then 1 over 2 is 0.5s. Good. So that's basically how it is. Of course, one thing you can do, as I was explaining in previous chapter, you go to the preferences and go to option and take this, apply it. Alright, so let's follow the tutorial again and keep a natural frequency of 1 radian per second. So then we are at 1. If I take it 10, for example, you can see now it will shift to 10. You see now it is the gain crossover frequency is at 10. So 1 over, basically 1 over 10 means 0.1 s. Alright, so here you have it in this format. If you wish to have it in other format, you can still also have it in other format, like for example here. So see, well, here it could be written this way, no problem, but you look at it how it's written in here, because I said I want my format to be natural frequency this way. And so if you wanted to read it this way, as the format we saw in the lecture, could be TS, or it could be 1 over omega. So both formats, as explained you in previous sessions, previous videos, all formats are equivalent at that. So just be aware of which format you want to use. Like here 10 over s plus 10, which is equivalent to this one. Because I picked natural frequency format now, I'm seeing it this way. Okay, so it's up to you at the end. Well, so it is at 10 then. Okay, omega is 10. Let's return to the omega, which is 1, as in the tutorial. So location is -1. What it means? It means location of your pole. Well, if you want a pole to locate it in the s-plane at -1, then you need crossover frequency equal 1. Basically because s plus 1 equals 0, then s equal -1. And here 1 over 1 means the 1 is your cut over frequency. Okay, so that's what it means. The location and frequency are almost the same. So damping equal 1. Why damping equal 1? Well, because this is first order system. It has no damping. It's not like it has no damping. It is like kind of real system. So it's real. One real, like assuming you have a second order system, for example, and second order system where you have two poles located at the same point, assuming. So in this case, your system is critically damped system, which means the damping ratio equal 1. Well, that's how it is here. At the end, you are adding a real pole, okay, in this experiment. All right, here you go. So what else in the tutorial? Okay, so they actually delete it. How to delete it? I click on, I go to my, and then I delete it, so it returns to the original look. Then they decided to add pole actually at 1 radian per second. So now, what if you want to add pole? Sorry, 0. Now, when we added pole, remember what's happening. The system will go to -90 degree and with 20 decibel per decade. So here is 20 -20 decibel per decade. As we saw now, that's the crossover frequency, which is the 1 radian per second. Crossover frequency, okay. And this is -20. So now, if you delete it, as we saw, we delete the pole we added, and we add a 0 instead at 1 radian per second, for example. So what you will see a 90-degree, actually plus 90-degree as you saw in the lecture, and plus 20 decibel per decade. So you see, and this is the derivative factor, remember from the course. And the derivative factor, as you see, it amplifies the high frequency. And usually noise in the system are high frequency. That's why derivative in practice amplifies the noise. So if that's my signal, wanted signal, and if your usually the noise are high frequency on the measurement, you have noise, these are high frequency. So the frequency between here is very high because period is very low. So this high frequency signal, when it goes to the derivative, it will be amplified, which is amplitude, this is the magnitude, remember, and it will get amplified, and therefore I may lost my signal. That's why derivative, it's not recommended by itself, so better to add a pole maybe to your system, so having a filter, low pass filter, to cut off the noise at high frequency. And if you go to our playlist channel, remember one time I talked to you about numerical integration, and basically you go to chapter 5, PID controller design, and I was talking about the PID numerical integration and why derivative term we don't likely like to integrate it numerically, and of course in analog way. Basically I recommend to go to the session 7 adds on, where we was explaining the library. Okay, so here you may find I was talking about the PID library also, and this session is connected to the wrap up session, which also theoretically I was described the numerical integration of the PID and convenient advantages, and here I was talking in particularly about the library itself. So I recommend to go over them again and to refresh your memory. Okay, and this session by the way was recorded, but wasn't live session. Okay, so then yes, so let's go to the tutorial. So what they could do, like for example here in this tutorial, they adding another controller at another pole at one, another, yes, pole at one. So it seems like 0.1 and 1, so they have 0 at, not at 1, 0 at 0.1. So maybe I can drag it to 0.1. Just I'm clicking right and dragging it to 0.1 to verify if it is 0.1 or not. Yes, it is somehow 0.1. Okay, so I can take it exactly 0.1. And then if I add a 0, right click, add real 0. You can do it this way, or click on the 0 on the pole. Actually I want to add as a demo real pole at 1, so that's the one basically, approximately. Okay, see what's happening here. Let's check if we are exactly at 1. Actually 1.11, so let's have it 1, and that's what you see. So now you see that at high frequency, now I trim the high frequency amplitude, so it is constant now, because when you added, you see a pole at 1. What's happening is, plus 20 with minus 20, they sum up. Logarithmic scale production becomes summation. Then they sum up minus 20 and plus 20, so they cancel each other, becomes 0. Okay, and same for the angle. So remember it was 0 to minus 90 to plus 90. So now after adding the pole, so minus 90 plus 90, it returns back to 0, and that's what you could see. All right, go back to the tutorial. So you could add another pole. Okay, and here you go. For example, you could add, if you wish, another pole. Like if I add it here, so now I will get, if you want to really attenuate too much the frequency, not only keep it same amplitude, but I have to want to attenuate more. So you see, now from 0 went to minus 20 decibel per decade. Also, the angle went to minus 90. So if you want to add one more pole, for example, so this is going to be minus 40 decibel per decade, and this is, will go to minus 90, minus 90, minus 180. Okay, so for example, I want here, and therefore here it go to minus 40 decibel per decade. So here was minus 20, here minus 40 slope decibel per decade, and here it goes to minus 180. Okay, so now we know how to use the tool, um, and refreshing your memory about how we are drawing actually body diagram. Okay, remember how we are drawing body diagram manually. So now we are looking at the effects, so we could remember them. Well, let's return back to our original code, having deleting all. Right click, delete poles and zero, at least as they are doing. And what they did, they add complex poles at 1 radian per second. So let's add complex conjugate pole at 1 radian per second. Let's make sure it's 1 radian frequency. It is 0.9, so it is 1. And now you see I have access to the damping, which is by default is 1, and real part and the imaginary part. If you look at it, I'm adding them at the same place. So this is a second order system critically damped because the two poles are real and located at -1 at the same location. So that's the location plus -1 plus minus 0 I in the complex plane 0. Alright, so that's the complex pole that I added with damping equal to 1. So that's why I explain why damping equal to 1. If my damping, for example, is 2, it doesn't take. Look, put 2 and it turns to 1. Why? Basically for the simple reason, because here, if you think why it doesn't take 2, it takes 1. But if I give, for example, 0.5, it takes. So what's the magic here? Actually, basically, it doesn't take above 1 because those are, when you click on this, you actually click on complex conjugate pole. Complex conjugate. So if it's conjugate, they could, so means they are at the same. That simply means that if that's your S-plane, if it's complex conjugate, so you should be at the same place here. So they have same real number. The real number is the same. Okay. When you say zeta equal 2, if I want to say zeta equal 2, why it doesn't take zeta equal 2 means your number are real but distinct. And if real and distinct, they are not conjugate anymore. If they are conjugate, they accept to be here, for example. The two poles are at the same location, the yellow and the blue, for example. So then it accepted complex conjugate. So then if it is like this, so it is zeta smaller than 1, between 0 and 1. But bigger than 1 doesn't take it for the simple reason that you clicked on complex conjugate, right? Okay. So now let's follow the tutorial. They added it here, and you look to your system 1s plus 1s plus 1. Alright, what else in the tutorial? So they take natural frequency of 10. If you take natural frequency of 10, what will happen? So now I take natural frequency not of 1, I take it 10. So then your real part is I minus 10. So you see natural frequency S over 10. 10 is the frequency, and this is a second order system. That's a second order system with real poles at minus 10. So that's why its damping ratio is 1. Yeah, nothing new. Let's continue the tutorial. Well, I put a damping ratio of 0.5. What will happen now if I take a damping ratio of 0.5? Alright, this is my damping ratio is 1, and what it means, if you go to your second order system, remember it here, I was computing the resonant peak, magnitude at peak, and this is, we define it as 1 over 2 zeta square root 2 minus zeta square. And I told you when we did system identification, if you remember, that zeta 2 you can neglect it. If you remember your PDF, I explained about system identification extra here. See how we get this? This is 20 log of 1 over 2 zeta, if you remember. So, and 1 over 2 zeta, why it is 1 over 2 zeta? So 20 log 10 of mr 1 over 2 zeta. I told you let's neglect, and most of the case, because zeta is between 0 and 1 and small, so power of it, you can neglect it with respect to 1. Then this is approximately 1 over 2 zeta. Okay, and knowing that the peak equal 1 over 2 zeta, and this is very important. Why? Because now 1 over 2 zeta, how much? If you compute to me 1 over 2 zeta, is in this case it's 1 over 2, because zeta equal 1, so 1 over 2. So then logarithmic of 1 over 2, log 10 of 1 over 2 is minus 0.3. And if you multiply by minus 20, so sorry, 20 log 10, that's decibel. So 20 log 10 of 1 over 2, so 20 times minus 0.3, it is minus 6. So then minus 6, look at it here, is somehow minus 6. Alright, so this is why I said it's important to look at the zeta. So now what if I take zeta 0.5? What will happen? Yeah, think with me. If this is 0.5, what will happen? So this is 0.5. If it is 0.5, see, let me return it back to 1. Return it back to 1. Okay, at 1, I have minus 6 decibel per decade. Sorry, minus 6 decibel. If it is, instead of 1, if I put 0.5, then the magnitude, if you wish, resonant peak 1 over 2 zeta is 1 over 2 times 0.5, so it is 1. Then 20 log of 1 is 20 log of 1 is 0. So then this is will be shifted to 0 if your zeta equals 0.5. Let's test if my zeta equals 0.5. What will happen? You see, it shifted to 0. Now, if I take small value, for example 0.25, I start having peak. Alright, and that's what we saw before. Okay, let's see, continue the tutorial. Yeah, so then we saw the effect of damping ratio. Now what they did, they shift the natural frequency from 10 to 1, for example. and let's see how this will help. So it was at 10, they put it at 1. Okay, and this is the natural frequency is at 10. If I put at 1, what will happen in this case? And you look to your system how it looks like now. That's your controller now. So you have a natural frequency of 10, damping of 0.25, and that's your real part and imaginary part. When you take the Z, and basically this is, it has the form that we are using in here. Alright, 2 zeta j omega over omega n, or if you wish, 1 over s over omega n square plus 2 zeta s over omega n plus 1. That's your form. Okay, that is your form. S over omega n, which is 10 square, 2 zeta s over omega n, which is 10 plus 1. That's the form that we are using because we said references and use natural frequency form. Okay, so what if I put the natural frequency equal 1? So this will be shifted from 10 to 1. Alright, so then it is 1. Natural frequency of 1, and this is my damping ratio, real part and imaginary part. So now look at it, it is at 1. Alright, you can put it 30 and so on, so play in this house. Let's see what's next in the demo. So they are playing with it 10, 1, 10. Okay, here they're using a different format in their tutorial anyway. In our tutorial, our format is different, like here. Okay, that's the format we are using. Of course, here you can see it this way in different formats like this, but in here the compensator you can look at it. Then if it is 1, we are like this. If we are 10, we are like this. So you see it's at 10. Themselves they use different format. Okay, so what if we add a 0 as they are doing here? So they add actually, look, a 0 at 1 radian at 10 radian per second. What will happen if we add 0 at 10 radian per second? Okay, let's add 0. Right click, add 0. You could do it this way, or as they are doing in the tutorial, this is 0 at 10 radian per second. First, let me make this at 1. Okay, and add 0. I will do it this way. Real 0 at 10. So what will happen now if I add 0 at 10? So this is the minus 20 decibel per decade, or minus 40 decibel per decade, will be minus 20 decibel per decade at 10. Alright, this is, and the angle, which is here at minus 90, or should be minus, it's already added the 0, right? It's already added. Let me delete it. Okay, so this is minus 40 decibel and this is minus 180. if you add the 0 at 10 to the power 1 at 10 radian per second, so here will go to minus 90 and here will go to minus 20 decibel per decade. So add real 0 at minus 10, and that's what you get. So it goes to minus 20, and this is go to minus 90, and this is go to minus 20 decibel per decade slope. You see this slope was minus 40. The slope was minus 40. See? If you continue the line like this, minus 40, this is minus 20 decibel per decade. Alright. Okay, let's continue the tutorial. So see, add 0 here so you can see the graph same as us. Alright. You can add pole. See what's the effect of adding pole. For example, they add it at 100 radian per second. You could add pole, and what will be the effect you could expect? Then will be again go to minus 40 decibel per decade, and this is will go to again to minus 180 degree. See, this will go to minus 40 decibel per decade again, similar to the first one. Because it was second order system, here you have two complex conjugate pole. Alright, and here it returns to minus 180. And of course that's your compensator now. So you have two complex conjugate pole at natural frequency equal 1. So that's the natural frequency of them, and damping equal to 0.25. So we can know that we have damping with the peak. So we can know it's complex conjugate, and they have real 0 and real pole. Real 0 is here, pole is here. That's a real 0 and at 10, and that's a real pole. It seems at 74. So I can add it at 100 if I wish. Okay. All right. So you can see this basically about this tutorial. Okay. Now in the next record we'll start talking about design with frequency response, or basically with Bode Plot, how to design controller via Bode Plot. This record, the actual record we are doing, was like a refreshment, okay, for what we did, but basically doing the analysis using MATLAB to fix the idea.